Okay. Now that we are done with garbage collection, so let's begin with the talk. So we have Bernhard Fischer with us here today, and he is a professor of applied sciences at the University of Austria, where he works primarily on IT security, but that's not what he's going to talk about today, at least primarily. So his talk will cover the principles of sea chart and marine mapping, with the goal of developing a free editable marine chart analogous to OpenStreetMap. So let's begin the talk right now.
This talk is something that you, I think, might not expect on a conference like this. So many topics are about security issues and hacking and stuff like that. So this actually is about sea mapping. So what does this have to do with security? And I tell you, this is included in the topic. It says safe navigation. So safe means it has something to do with safety. And safety and security is somehow really familiar terms, and it depends on the language you use. So in German we have the word Sicherheit, and it expresses actually the same. So we cannot in German differentiate between safety and security. That's good, because if we say Sicherheit, then we mean all of them. In English we have to say security is this and safety is that. So I came to the OpenSeaMap project because, I must press here. Okay. Because, well, what I'm doing, I'm in the past did, let's see, several years training and instruction on yacht sailing, mainly in the Adriatic Sea. And in parallel, I'm, as he said, I'm a professor at the University of Applied Sciences in Austria, where I deal with, let's say, security issues, mainly in the network area and system level programming and stuff like that. So actually I'm an IT guy, I'm not some marine mapping guy. But because of those two, let's say, interests, my personal interests, it's clear that I joined this OpenSeaMap project. So, and in the first, let's say in the first weeks when I came into this project, I was really enthusiastic about doing stuff and entering nodes into the database and creating everything is fine. But it turned out to be much more complex than just putting some nodes into the database, specifically when we talk about sea charts. There's a big difference, and I will elaborate on the difference of, let's say, a road map and a sea chart. There are big differences. Well, as I said, I'm an IT security guy, so maybe some of you remember me. 2 years ago I had a talk here about OnionCat. It's anonymity software and stuff like that, so a complete different topic. Okay, so what are the difficulties? No, what I'm going to talk about is, so first I will give you a brief history about surveying and cartography. Then I will talk a little bit about charts in general and sea charts specifically. And then I'm going to talk about actually my part of the project. It's the lights and depths problem that we have. So I will a little bit elaborate on that. And of course there are security and safety issues with all those things. So that's why I chose to give a talk here. So in my opinion, usually, so that's also true for myself, IT guys usually tend to, let's say, if you catch up with a specific topic, the first thing is you try to understand it, so you read a little bit on the web, and then you're going to write software. And then everything gets worse, because you dig into this software problem and you miss all other problems that are associated with the problem, with the real problem. So you miss everything. So I can just suggest to not dig too early in the software actual engineering process. Start to understand everything around the problem. Maybe I should tell what I am not. I did neither study cartography or geography, and nor am I a geodesist or something like that. So all I will tell you now is what I learned from myself to understand the real problems of sea mapping, of marine mapping, okay? Because actually I'm an IT guy and I'm going to write a piece of software later then. Okay, Well, may we ask why creating a free sea chart? Why should we do this? Some of you, I think, are familiar with marine mapping or with, well, cruises, holiday cruises, whatever. If you use a sea chart and it's not an official one, then it may say on the top, do not use for navigation, because it's unreliable or untrustable sources or whatever. So if we create a sea chart and we cannot trust to it, we should put a sticker on it and say, please do not use for navigation. But actually then the chart is useless. It's completely useless to have a chart which says do not use for navigation. I need a chart that I can use. So there are two options. Either drop the project because it's useless, or the other choice is make it high quality so that I actually can really use it for navigation. And you will see there are differences in navigating a car and navigating a vessel. Okay? So, of course, I'd like to pick the second choice. Okay, sources for navigation of a vessel. A sea chart is not everything. So there are many other things. Like, for example, we have, of course, the sea charts. We have a list of lights. It's a list that covers all lighthouses and stuff like that. We have a handbook of harbors and coastlines, which describes verbally how the coastline looks like to find a specific bay or port or whatever. We have a list of radio stations which you need for getting contact with VHF radio or whatever. We have tide tables, we have astronomical almanacs, we have the notices to mariners which cover errors and corrections for errors that are actually in some of those sources that we use. Well, one other question may come up. Is this about, let's say, holiday cruises, or is it about commercial shipping? I say both, of course, because there is no difference. Of course, in commercial shipping, we can assume that people working there, so captains of big passenger ships or ferry boats, that's their job. So they're very well trained, they know how to cruise and how to use these materials. But even in holiday cruising, I need to use the same and understand the same material, and it's no difference if the material is inaccurate for a professional and for a, let's say, holiday cruiser. So it applies for both, of course. Let's have a look at the history of seafaring. So there are some famous guys. There are hundreds of famous guys. I just picked out some of them. There was Henry the Navigator. Well, actually, he was the one who discovered the whole coastline of Africa. The interesting thing about it is that he actually never was on a boat. He was just the organizer of those explorations. Then we have Christopher Columbus. I think most of you know him. He discovered, well, accidentally something. It was not America, but okay, we know. Then we have Vasco da Gama. He actually found the way to India, which was the goal of Columbus. Then we have here Ferdinand Magellan, who circumvented who was the first captain to circumvent the whole globe. Unfortunately, he was killed somewhere, so he couldn't finish his trip, but the boat arrived again. And then we have James Cook. He was a brilliant scientist and a navigator also, and a good captain. He did many, let's say, explorations around the globe. What did they do? Actually, they tried to find some new countries, but they also tried to build maps of what they found so that somebody later in history can find this place again. And how did they do this? Well, of course, they used a lot of astronavigation. Astronavigation is this part with measuring something with this device here. It's the well-known sextant. It looks very complicated. Actually, it's just a device for measuring angles and what these navigators do. They usually measure the angle between the horizon and some star or whatever, somewhere. So what they need for astronavigation is they need books which say, okay, this star is at this time, at this place, at this angle, so they can calculate back where they are, okay? Then what they very often need is the measurement of time for accurate positioning. They needed the time, and it was actually a real problem then. They couldn't measure time in that sense that we understand. We can put it on milliseconds or microseconds. They couldn't do that at all. So it was really inaccurate. And even today, who knows how accurate we can determine the position on the ocean by using such a device today? Just guess, say something. How much? A quarter of a degree, yes. That's something about that. So it's a few nautical miles. So we can actually not on a meter exactly. It's a few nautical miles. So it's a huge area today. They, of course, use trigonometrical survey, which means I have a fixed location, which I know the position, and I measure the angle to some other place. And if I know the distance, then I can do some mathematical stuff. And of course, what they needed is a really important thing, and that's the worst of all that mapping stuff, is the true figure of the Earth. How does our Earth really look like? Okay, so I think we can agree that it is something like a sphere. Everybody knows that today, but they were not so sure about that fact. So if we go back in history, we find suggestions for models like this. It's not a joke; it's real. So you can read it in literature. In the Greek, philosophers suggested that it must be something like a cylindrical body, and it turned out to be, well, to have some oddities, and then some other philosophers suggested, no, it must be a cube, actually. But even this was not really a correct model, but in the times then, it was really easy to explain something, because if they couldn't scientifically explain something, then they just said, okay, it's mysterious. Something handles these oddities up there. So it was easy. That's not possible today. And then somebody suggested that it must be a sphere, and this guy was a Greek philosopher called Eratosthenes of Cyrene. He was the first who really said, okay, it is a sphere, and he did this well-known experiment. So it's a small picture. He did an experiment. If we assume there is the sun, and he has a tower here, and there's a hole, and the sun has parallel light. That they knew that it has parallel light. So if it falls down here, we know exactly the sun is on top, and then we can measure the angle from how, let's say, how curved this tower on the other side is. And if then we do a little bit math and can, well, roughly calculate the circumference of the Earth, which is important if you have some degrees in measurement and you want to convert this to an actual distance, okay? Interestingly, he was very accurate for that time. He missed it about plus minus 10%. Plus minus 10% is because we today actually do not know which unit of distance he then used. So we actually do not know what's the distance he used in this time. So it's just an estimation. Okay. Things got better. Dark ages came, and people suggested, for whatever reason, the disk world. Okay, it's like this. Okay, it's everything on a disk, and if you go too far out, you fall into the deep ocean around everything, and stars are fixed somewhere. That's a nice model. It's really a good model because on a plane, everything is very easy from a mathematical point of view. It's a really easy thing. But unfortunately, well, we know what happened. This is not the correct model as we know today, okay? And if we go a little bit further in history, there's those two guys, Christian Huygens and Isaac Newton, I think most of you know very well. And they suggested, no, the Earth isn't a sphere, it's something like an ellipsoid, and it's called the ellipsoid of revolution. So it's a a ball if you just squeeze it a little bit, something like that. Okay? So it's a perfect model because it's a mathematical model and you can do calculations and math with it, okay, very easily. But it became worse. There was another very famous guy, a German mathematician called Friedrich Gauss, and he suggested that it is not an ellipse of revolution. It's something like this, okay? He said, no, it is actually not a mathematical object. It is something like this celeriac here. It's a picture or a potato or something like that. And we can determine the real body of this object by measuring the gravity. So he said the true figure of Earth is expressed by a surface of equal gravity around the Earth. And we can easily, let's say, measure this by using just a balance and measure the gravity, and then we can, let's say, draw a picture or describe it somehow in big matrices that have the terms of location and gravity, stuff like that, okay? But unfortunately, this is an irregular surface, so it's not mathematical anymore. And this picture here, actually I took it out of Wikipedia. It looks there similar, okay? It combines all that what I told you now. What we see here is, on one hand, this pink line here, it's called the geoid, and that's the actual figure on an equal gravity base, okay? That's what it really looks like. Then we have here, this dashed red line is the ellipsoid. The ellipsoid is the mathematical model of it roughly looks like, okay? And then the green line here is the continent. We see the mountains and stuff like that. And the blue one is the ocean. And we figured out that, figured out that that the geoid surface is roughly the surface of the oceans if they are in equilibrium. That means they do not move, and there's nothing like tides, you know, from moon and sun and stuff like that. So if they're really completely silent, okay, then we have this geoid surface. But of course, where the mountains are there, we have no oceans. It's a little bit difficult to determine. And what you else can see in this picture, that the ellipsoid on some points meets the geoid better, and on some points, it's here you see it doesn't match at all, okay? It's completely different. So there are differences between the real figure, the geoid, and the ellipsoid, which is a mathematical model. Okay, as I said, it's an irregular surface. What they continued in history is that this ellipsoid of revolution is a generic model, but they found out that we can calculate, calculate different ellipsoid models that fit on different places on this world better or worse. So what happened is actually that we have different ellipsoids, and those are called the reference ellipsoids. There are several of them. I just picked out a few of them. There is this Bessel ellipsoid, which is from 1841, which was mainly used, or still is used in parts of, or most Europe. Then we have this Graskovsky ellipsoid, which is from the former Soviet Union, which covers their surface better than ours. And then we have the Hayford ellipsoid of 1924, which became later an international ellipsoid, and it was widely used in America because it fits better there, okay? So we have different ellipsoids in different places on the world, and the problem is if the figure is not matching, if we have different figures and we use same coordinates, that the coordinates based on those figures might not match. So if I use a different model, then I give you the same coordinates, and if you use either this or the other ellipsoid, you will find a different actual location, okay? Okay, let's have a look at the World Geodetic System of 1984. It's a WGS 84, I think most of you know. This actually is a system that defines a specific reference ellipsoid. It's not one of the others. It's another model that tries to fit best in the whole world, somehow like that. And it contains a model about the geoid. It's called the Earth gravitational model of 1996. And this is, let's say, a mathematical model which tries to describe this, let's say, irregular geoid surface that it is in reality. Okay, so those both are combined together, and we call this as a geodetic datum. And then we can put coordinates on this by defining, let's say, reference points, and we say coordinate reference system. That's actually, I give you a coordinate in 47 degrees, something like that, and let's say where we are here, 13 degrees east or something, roughly. And then we know, okay, it's exactly this place referring to this reference system, okay? But it might be different on another reference system. Okay, yes, the coordinates, we know about how this works. I think most of you are familiar with that. Question?
How much difference would it mean in terms of meters or kilometers or whatever?
I had this on the last, I had this somewhere on some slide. I will tell you, it's about 100 meters if we have the VGS84 system, okay? So, it's on the next slide, I think. Actually, coordinates are always three-dimensional, and that's the problem. So if we give a coordinate in latitude and longitude, then it's two-dimensional, okay? But every object really has a third dimension, and this is the elevation. And the ellipsoid figure is nice as long as you just want to describe a two-dimensional figure on the same elevation. But as soon as you want to describe elevations, you need to know the actual height, which is based on the geoid, actually. Okay? It's the point of gravity where we are. And that's why in VGS84 we have those two different models. And if we compare the ellipsoid used here to the gravitational model, we can see that there is, depending on which location you are on the Earth, roughly, it's not 100% exact, but roughly about plus minus 100 meters, okay? And that's pretty much, okay? That's really pretty much. Specifically if we talk about CMAPs, but we will see this later. Okay, and then there is the next problem, how to get this real picture here of Europe onto a flat piece of paper. That's a problem that is very well known, and that's what we call a map projection. We try to let's say, project this sphere somehow on a piece of paper. There are several models available. They were, let's say, mathematically described during the last hundreds of years, and one that we use in C-charts is this Mercator projection. And this fits very well because it preserves the angles, and if we have small scales at least, then it also preserves, roughly preserves distances. That means there is no perfect projection. As soon as we try to put a three-dimensional object onto a two-dimensional plane, it gets distorted in some way, and we can just choose which distortion does. Well, which distortion is the best that we can, the best trade-off that we can take for a specific use case. So depending on the use case, you choose a different map projection. So for C-charts, we actually have this, and preserving angles means that I can put a triangle on my map. So here I have a map for all of you. That's a typical C-chart. I have it in the slides later. And you can put an angle, a triangle here, and actually measure, okay, this is 35 degrees something, okay? And it's independent on where on the map you put the triangle. It's true for all positions on the map. Okay, now here we have a C-chart. That's what I showed you here. For all of you who has never seen a C-chart, a real C-chart before, please raise your hands. Okay, so Most of you are familiar with this. For those who are not, we have a lot of veto information for a navigator, for a captain, or somebody cruising with a vessel. So what we see here is there we have a light. We have several lights. Those are the parts with this pink shape here. Then what we see else is we have depths here. Well, the white part is the sea. The yellow part is the island. We can see here the blue one is shallow water, the white one is deeper water. Then we have what we see here, for example, those are some underwater obstructions, some rocks or whatever. Then what we see here, for example, there is a wreck of a ship that was abandoned somewhere. Okay, so many different information we have in here, and all of this information is vital for navigating, for safe navigation of a vessel. Okay, so let's compare a little bit the difference between a road map and a sea chart, or actually compare navigating a car and navigating a boat. There are big differences. The first one is navigating of a vessel is not limited to roads. So actually you can navigate with your car even without chart. If you want to go to, let's say, Munich, you just, there's somewhere a highway, you enter the highway and hopefully there will be a sign that says go this direction. And actually you just have to follow the road. There's no danger in between, of course, hitting another car, but okay, that's your own responsibility. You cannot get off track, okay? For vessels, this is not true because you can navigate everywhere in the ocean. There is no road. Then, what we have a big problem is that underwater obstructions are invisible. They are invisible, and if you put a guy on the bow of your boat and to tell him, look into the water if there is something, he might not see it if the sea is a little bit rippling or rough or something like that, so you can completely forget it. So that means you need to know that somewhere is an obstruction. And by, let's say, using this chart, you can find a correct course to not hit this obstruction, this underwater obstruction. There are no road signs that tell you go this way to this harbor or whatever. And another difficulty is that vessels can't just stop. They can't just stop and get out and ask somebody, excuse me, can you tell me where is the way to this? They can't just stop. There's always wind, stuff like that. And another thing is that harbor approaches might be really difficult or at least time-consuming. With a car, it's completely easy. You go there, you stop the car, you get out, you ask somebody, you get in, go away. That's a few minutes. If you do this with a boat and you're somewhere, you have to approach a harbor. Until you're there, everything is slow. 1 hour is lost. Then you have to find a place there somewhere, a parking lot. So time's lost again. And then, okay, so it's really difficult. So it's better to know in advance where to go and where you are and where you should not go. So that what I said here is data accuracy is a must. This nice picture I found on Xcasity today, 731, you can look it up there. So it actually explains what I said. So there's somebody sitting and he says, well, there's nothing around, but if you look underwater, there may be very much. And well, as we can see, somebody abandoned his ship here for whatever reason. Okay, a problem is now that we have different reference systems. Because we have different reference ellipsoids, there's the GUI, some did not use it, some used it, whatever. There are several systems and you can combine them in any way, theoretically. And what happened is that nations combine them in the way that it fits best for them. So we have different reference systems for different countries. It's different in Croatia, it's different in Italy, it's different in Germany, it's different everywhere. And all of them use coordinates in sense of longitude and latitude, but we cannot just compare it or set them equal because they are not equal. They are different because they refer to a different system. Here I have an example. So you may ask what actually is the difference, and the difference might be pretty large. So for Croatian, that's this chart I have here. It's 1.28 degrees east, and if you calculate it, something like 370 meters. And that's pretty much. If there is a rock and I fail it, then, or I hit it, then it's bad. So 370 meters is very, very much, okay? So this difference actually is the difference between the Croatian system and VGS 84, okay? So if we take a coordinate from this to that, and we do not transform it, then we got this error. That's what this means, actually, okay? Okay, let's go on and create a free C chart. So, a free C chart. It's easy, just go out there and with your GPS device and pick up objects and lights and everything like this. Okay, that's impossible because, well, our plant is really big. So people doing this chart, they are doing this for hundreds of years, and they did not start yesterday with this chart, okay? So, and what else? We are not just allowed to, as you know, copy this data here, because usually it's copy protected somehow, okay? It's different from one country to the others. We know from OpenStreetMap project that some countries give their national official data to them. That's really nice, but we cannot force them to do so. So some do just not. And as I told you, chart accuracy is a really big challenge because of those different reference systems and because it's extremely important for vessels. For cars, it's actually not that important if the road is here or if it is, let's say, 50 meters on the other side. Because actually when driving the car, you see that here is the road and you go there independently of what actually your navigational system says, okay? So you follow the road. On the vessel, it's different. You have to follow your navigational system, which actually is your chart because there is no road. So it's absolutely important that you have accuracy, and it's a big challenge because of those much oddities with those different reference systems and whatever. So let's talk a little bit about security. I have this paradigm, it's called CIA, and some might have followed the talk of DJB yesterday evening. So he raised this topic again, also in the context of cryptography. So this paradigm is generally used in literature for, let's say, IT security, and they say in literature that if your system, or on the other way, your system is secure if you meet those three issues. So it's confidentiality, integrity, and availability. And if we try to apply this now to the OpenStreetMap database, I think we fail in this point. The OpenStreetMap database is a database which, let's say, contains all the data. It's one unique database, and we pull out from this database the data that we need for a specific type of map. So there is, of course, the street map, there is a mountain bike map, there's a sea map, there is the whatever map, okay? And it's all stored in the same database. The problem is that if we look at this conference, we talk about surveillance, we talk about data retention, we talk about them and they are doing bad things and we are the good ones, okay? Or something like that, okay? I don't want to get political, but this is what this is about, this conference here. And then we are all experts in IT security, and we know how they watch us and stuff like that happens. What do we? We actually are completely different from them because we come in peace. We build a database, like the OSM database. Everybody has access to it. You go there, register your account, and go ahead and edit the map, which is completely free. And this problem is inherent for several projects, not just the OpenStreetMap, okay? This problem was raised at several talks already in this conference. For example, the WikiLeaks discussion about who can we trust, who actually filters the content. Can we trust that he filters the right content? Or similar problems like the Ushahidi. Can we trust that they really do right? Can we trust ourselves? So that's the model that we apply currently for OpenStreetMap. So we trust that no problem happens, so that there is no, let's say, malicious suspect that does not accidentally, that does really change data. And this, I think, in my opinion, this might be a problem for OpenCMap, because OpenCMap, or in general, a CMAP is vital for navigation, for safe navigation of a vessel. And we should somehow make sure that we can trust the data, that we can say, okay, it's reliable, it's correct, it's confidential, it's inter, and it's there, okay, it's available, okay? So I think, unfortunately, I don't have a solution for this problem, but I want to raise it again, yeah? I think we need some more stringent trust models if we are going to deploy serious sea charts, because we depend on it. Life depends on it. And if you, let's say, crash your boat, just, let's say, some holiday cruising sailing boat, then hundreds of thousands of euros are lost. And if you, let's say, people get somehow hurt, then you're in millions. So you really depend on this chart, and it must be correct. And as I told you in the beginning, if you put there a sign that says do not use for navigation and actually it's useless, then we can stop the project, okay? Okay, let's go ahead and look at how can we gather information. How can we now gather information into this C chart in such a way that it is reliable? Well, there are several options. This means use data that is not copyright protected. That's what I mean with this, okay? So public data or not copyright protected data. We can let people walking around with their GPS devices collecting data, entering it. And other systems like, for example, and that's actually my part of the project, it's the import of the list of lights. This is, most of you I think know, the list of lights is a book published from several spatial agencies on the world. It's a book like this. It contains all lights, and luckily the United States Spatial Agency publishes this on the web in kind of PDF documents. And we can, let's say, grab out this information. It's what I'm doing. So I grab out this information, but there are several problems. The positions are not really accurate. It's to 1/10 of a minute. It's about 180 meters. It's not very accurate. And we have this problem of different reference systems, actually. We do not know to what this information refers. We have people in the background which are in contact with the IALA and other authorities, but nobody really knows who has what reference system and how these coordinates are referred to. Okay, I'm doing this stuff. It's a lot of Perl scripting and stuff like that, and the result is currently, I show you here. That's what I have currently. So it's a list of lights imported into the OSM database. Actually, it's not in there at the moment. I have it just as local file, and it looks pretty good. Unfortunately, you see United States is missing because they use their own format. It's not compatible with my tool. Okay. What I'm going to do is I will put this in a, let's say, site database where people can edit it and correct data because it's actually not correct in that sense that we need for a C chart, okay? Another really difficult problem is the depth. Measuring depth is really important for a vessel. I think, that's my opinion, we need, let's say, an accuracy of 1.5 meters, half a meter, something like that. And it may be, you may enter some port if there is half a meter more or less. So it's really important. Actually, if you are hiking and you're on the top of a mountain, it makes no difference if the mountain is 10 meters higher or lower. But on vessels, there's a big difference, because if you miss it at, let's say, such a small distance, you may crush your boat, and that's expensive. The ocean surface is in permanent movement. We know this. We have winds, we have tides, we have currents, and also the seabed may change because of currents and permanent movement that's going on there. So that's difficult. How do we actually calculate the depth? If we look at this chart, it says it's let's say something 60 meters. But is it really 60 meters there? How do we correct this? And there is a mechanism. It can't be calculated if we know which time it is now, which date we have. We know our position, and we know the chart datum. I will come to this then. And we know the chart depth. Then we put this together with tide tables. We shake it well with the calculator, and then we can say, okay, at this location is currently this and this depth. Okay, if we go the other way around, we can then measure something and put it into a sea chart. This picture, well, roughly describes what the chart datum is. That's what I told you before. So we know this reference geoid. It's completely useless. It's 100 meters different from the real geoid, okay? But the real geoid is if the oceans are in an equilibrium. That's a theoretical model. That's not true for the reality, okay? So what we define in sea charts is we have a virtual 0 point, 0 sea level. And there are different 0 sea levels here that are used in different charts. Some charts use this, some charts use that. And you have to look and read what your map says. What's the depth referring to? Well, so there are different chart datums to which the depth actually is referred, and that's what's shown here. So the map actually gives you this information. If you'll read it in a map, then it says, okay, here is the depth referring to our chart datum, which is one of the 3 from before. And your boat is actually, well, above or below it, somewhere, and you can calculate it by using those stuff. So if we go the other way around, we need to actually measure the depth. Then we calculate it back, and we could put data referring to a specific chart datum. The problem is we need a chart datum. What I mean is we cannot just put a node in the OpenStreetMap and say 3.7 meters. That's completely misleading. It's dangerous to do that. Nobody knows to what this 3.7 meter is referred. We have to define all of those things here in advance, and then we can put in a node and say, okay, it's this and that depth actually. Okay, so let's come to an end. What's the conclusion? Sea chart surveying is not really trivial because of all those oddities and all those real-world problems. And one thing is that, again, data accuracy is really a must for a chart. Otherwise, it's completely useless. Sorry. Well, and then again, I want to raise this trust problem. That's really a big problem. So in the current state, everybody can edit, and I think this might be a problem in this sense of data accuracy and trust that we need from a sea map or sea chart, okay? So, well, because thoughtless editing may harm people, yeah? You hit the ground somewhere, okay, it may create dangerous situations. So what can you do now? Actually, there is lots of work. As all of those projects, I need people that do a lot of work. There's not just programming, as you see. There are a lot of different problems that are associated with programming. Of course, we need also programming, but as I say, we need brain power to just think about those problems. Editing map, programming, scientific power on research on calculating models of water depth, of tide table, stuff like that. That's all, not everything is public. Well, and that's from my part. I hope that I could enlighten you a little bit about the oddities of sea chart surveying, and that it's not done by just putting notes into it. We have to do some work in advance before we can really put information into the sea chart. Okay, so it's your turn now.
So with that, let's thank the speaker and we'll take questions from the audience and possibly from the IRC.
So, okay, so I'm not familiar with the data structure on the OpenStreetMap, but one question I had is there, for any given location, is there, well, not even a location, is there a way to express levels of known uncertainty with notes and or to have multiple pieces of information associated with a particular...
Yes, it is possible. So it's a complete, let's say, not perfectly, some kind of object-oriented model. So you can put nodes there and add as much as information as you like. So I can put a node in there and make a note and say, okay, this node is somehow unreliable, or I'm not sure, or I put this and that and that. But the problem is you have to see it's not just this part of the planet. So it's a really big planet, and if people are going to start entering hundreds of thousands of nodes and everybody chooses his own random tags for expressing something, it gets a complete mess. So I think we should define something in advance.
I'm suggesting actually like a more formalized, almost mathematical method of expressing uncertainty on a particular piece of information, so that whenever you say this underwater obstruction is here, you're saying it with error bands, saying it, for the amount of information we actually have, this could be from here to there, and instead of being a very precise point, it's a very broad piece of information, not some meta tag off to the side, but like literal mathematical uncertainty.
That's maybe a good idea to let's say invent some new uncertainty tags where we can describe how certain specific location is referring to a specific location. But again, we have to need to let's say predefine this tag. So, and this, in as far as I know, it's not easy to find a consensus about which tags are actually used to describe which attribute. Questions somewhere?
Yes, so some questions from the ROC. So first question, from what sources do you want to get the depth information, since it is illegal for anyone, at least in Sweden, to measure the depth and to share it?
Okay, that's a good point. I didn't know that it is illegal in Sweden to measure depth, but that's not true for all countries. So maybe we have a specific problem in Sweden that we should solve somehow separately. So, but for the rest of the world, let's say there are countries like Germany where we have, with the Hydrographic Institute, maybe we get some, let's say, cooperation where we can get data. That's not sure, maybe, okay? On the other hand, we are trying to build some devices which makes it easy for, let's say, holiday cruises to measure depth in such a way that's correlated with coordinates, that we can put it later in a database, in some database that corrects it, does all this tidal correction mechanism, and then puts it somehow in the OpenStreetMap database. Actually, this is an ongoing project. It has, the depth project has no results now, but we're trying to work, and I'm glad if somebody is would like to join us here in this specific point.
So this really leads completely to the second question. Do you see the finish, the end of the project, so that there will be a product that you can really use?
Well, that's, in my personal opinion, it should become a product, maybe for free, whatever, a really useful product. That's what I said in the beginning. I think it must become a useful product like this official map here. Mm-hmm. Otherwise, we can drop the complete project. Then it's useless if it's not accurate. It should become like this. Okay. That's at least my personal intention.
And the next question was, is already a navigation software available, for sure open source, that can do work with OpenStreetMap?
Well, it depends on what you mean by navigation software, but there is software available which renders the chart where you can see all lights that are already in there, all, well, let's say navigational aids that you have on a real sea chart. There is software available, yes.
So it is also possible, in this time possible, to show the depth in the open sea maps?
No, depth not. There is no depth information currently. There is no
Okay.
depth information
So
at all.
it's still in the
So
collecting.
I know
Okay.
there are some depth tags in the OpenStreetMap database, but I say they are dangerous. You should ignore them.
Okay, looks
Okay.
like most are done properly.
We have another question.
Yeah, I have one question about the sounding of depth.
Okay?
And I think because it's really important sometimes the meteorologic, the weather informations, because they have an effect of the depth, especially, for example, in the Baltic Sea. And do you have already approach for collecting the necessary data, or example, the frequency of sounding? Because sometimes it differ if the bed of the sea is very sandy or something like that.
You mean if we already have an approach of how to sound the depth?
Yeah, how to solve the problem that you can calculate the meteorological factors during the measurements?
Well, the meteorological factors that's a real problem. Actually, I don't have an idea how to solve this problem. What we can solve is all this mathematical process of tidal correction and stuff like that. Okay, the rest of the sounding, the sounding offset that comes from weather conditions is something that I don't really have an idea how to solve this. So in my opinion, the guy that is actually sounding may take this somehow into account, or maybe we put some button that there was strong southerly winds, and if we know the position and we're in the north of Adriatic, then we can assume that is half a meter above or something like that. It must be something like that. So because if there are weather conditions, usually they behave always in the same way. So you know in a specific port, if there are southerly winds, then the water is higher or lower or whatever. So they do not change. But we first should then collect this data in advance, that we know, okay, if we have southerly winds, then there is half a meter plus or minus or stuff like that. But it's really difficult. So sorry, I don't have a solution.
Okay, thank you.
Do we have any more questions? Okay.
Hi. Isn't there a problem also with the GPS data, with the accuracy that you get from certain devices in terms of depth or elevation, that satellites and stuff like that don't supply the accuracy as they do for, let's say, military data?
Yes, there is a problem. First, you should never trust the elevation data that you get from your GPS device. It's completely unreliable. So we should not trust on at least the elevation. Referring to the coordinates, the latitude and the longitude, I think it's, if you have a new modern device, I think it's accurate enough. Because if you're somewhere in the middle of the sea, you usually have very good, let's say, reception. Yes, you see all satellites, so it's pretty much accurate. And it's not really interesting. It's if the rock underwater is here or 5 meters beside. So that's not the accuracy we need. So because you should always, let's say, leave 50, 100 meters beside your rock that you're sure that you do not hit it. And on the other hand, if you're in a port sounding depth, then actually you're not navigating with your GPS device. You're navigating with your eyes. You do not enter in, let's say, like a submarine, the port. So you see it actually. And if somebody sounded the depth in the middle of the port entrance, and it says 3.7 meters, then you know where it is. It's actually unimportant at which real geographic coordinate this is. Okay?
Which other navigational aids or helps are you planning to enter into the database? I was, for example, thinking of magnetic declination and magnetic anomalies, which if you want to have the head, correct the heading of the boat and know in which direction.
Actually, as far as I know, we never thought about magnetic information, but it's a good point. We could.
Yeah, there are anomalies where
Yes,
the
I know.
magnetic-
I know there are
Yeah.
high deviation somewhere,
Yeah.
but
15,
as far
20
as I know,
degrees, yeah.
nobody cared about at this stage. But so if there's somebody out there, bring information into the database. We can put everything in there, of course.
Are there specific areas that you're using to create kind of a beta version of this, something that's actually testable and usable at this point?
It depends on the region that you are. So some areas are surveyed very good, like the northern coasts of Germany, for example. And some areas are really, let's say, at the current moment, useless, like Croatia. There's not much information in there. So it depends. You have to go at the online tool and look if your specific area is covered or not. So, and of course, I invite you to put information there.
Hi. There was a space shuttle mission a few years ago that used radar to map the world at a really high resolution. And as far as I know, that data is available, at least commercially. Maybe there's a way to get funding or to somehow involve people who have access to that data. Did you look into that?
I didn't know that. Maybe we can do this. So actually, to get it right, it is the OSM OpenStreetMap database. So everything is therein, and this information kept therein is not limited to to CMap. So we use the same information, of course, like OpenStreetMap and all these bicycle maps and whatever there is. So everything is there. So currently, at the current state, the planet file covers everything from every chart, and the coastline is on some parts of the world very inaccurate. So if somebody finds a way to get this data, it would help all of those projects, not just OpenCMap. For my part, I didn't know about this, so maybe we can, I will talk to our guys, maybe we can find it, but it goes also to all other interested mappers here that do other charts, because it's for us, for all of us, a good thing to have accurate coastlines, of course.
Do we have any more questions?
Okay, there's one other question. How much information is it possible to actually get from the departments in different countries that already handle the measurements?
How
much information is it possible to actually get from the departments in different countries that already handle the measurements? I have no idea, sorry.
I think it is how difficult it is to get additional data from different countries like this. So the question, I think, to repeat it, the question is, how difficult is it to get data from countries that handled over data or not, something like that? No? So actually,
I understand it this way. In many countries, there are authorities which have data, measured data, and the question is, how much information, how much data can you get for the different countries? Maybe difficult or not so difficult?
That's completely different. There is no generic answer. It's completely different, and it depends on the country, on their mindset, on their policy, stuff like that. So in Germany, it's actually, I think there are some laws that say this is public data, and they should give the data to you if you request it. That's what I know from Germany. So if they have data, it is public data because it is the country of Germans, so they can go there to the authority and say, please give me this information. But that's completely different for every country, so there is no generic answer. Some might give it to us easily. Some already did it, like Netherlands, I think they give it, and some other countries. Some will never give information out, and some might not have any information.
So if there are any more questions, I believe Bernhard will be around at the Hack Center, so
yes,
I
of
think
course.
the questions can be directed
If you have additional questions, come down to me in the Hack Center.
Yes, that'll be all. So let's thank our speaker again, and thank you.